So I am Rob Feldman, and this is Ryan Friedman, and we've been at National Instruments for I've been at National Instruments for about 11 and a half years, and Ryan's been at NI for about 12 and a half years, working on architectures, and so I guess we average out about a dozen years. We're going to talk to you a little bit about what we do internally at National Instruments. Over my tenure at National Instruments, I've deployed several products to our manufacturing sites that span from SMIOs, DAC cards, C-RIO cards, R-Series cards, just a whole bunch of different stuff. And I've been working on our RF products for the last six or 7 years. So any RF product that we've kind of released over the last few years, I basically have been involved in. And so we have a lot of internal knowledge on. Sorry, my watch has an alarm going off. So we have a lot of knowledge that we want to share, and we have tried a lot of different things in LabVIEW that either works or doesn't work. And we eventually created this framework that we're going to kind of show you bits and pieces of, and it's kind of more of a deep dive. And then hopefully you can kind of understand how to, maybe you can take this back to your own companies and you can learn how to develop your own HALs and MALs. So real quick, we're going to kind of breeze through the first couple of slides, which is why you want to create a HAL and MAL, because that way we can deep dive into some LabVIEW code and actually see how we implement stuff. At National Instruments, this is what a typical project would look like. As the project starts, we call it V&V, which is a lot of benchtop testing, and so this would include someone getting a board, probing it with a DMM, a logic analyzer or something, and just kind of making sure that it has some measurements, that it's coming up correctly and so forth. So there's a lot of manual measurements that are being done here. But at the same time, we also want to put it in the temp chamber, look at its characteristics of its data over different temperatures, so when you, our customers, get the product, it works fantastic. And this is the group that I work in, is the test engineering group, and we're kind of look more on the production side of things. At some point, the project that we're working on becomes mature enough where we can start deploying a test solution, which will be deployed to our manufacturing floor. It has its own unique careabouts as far as challenges. Generally, we try to implement switching, custom fixturing, and so forth to interface with the product that we're looking at. And then along the way, we have to support this in our manufacturing environment for several years, and so that also introduces new challenges. So you have to, things break, there's new technologies, or in most of our cases, when an instrument that we're currently using goes EOL, how do we easily swap that out in the future? So we have to be able to look forward to these challenges. And then at National Instruments, we also have a third part of the testing for a project, which is the metrology side of things. So this would be like CalExec, or when you send a product back to us because it's broken, how do we fix it, right? So this part of the project, as far as the time goes, could be greater than 20 years. We support most of our products for several years, and based on the contracts, especially with DoDs. And so each one of these each one of these domains or silos has interesting careabouts. Generally, metrology, as an example, some of the challenges they have is when they go to a Cal lab, they're testing a product, and at some point they want to swap out a different Cal standard. So, of course, I'm in the RF world, so I'll use some RF examples, but this would be where they want to swap out a different power meter in line of testing, or a different DMM, if you will. And so you're kind of worrying about the uncertainty of the instruments and the measurements. And then on the V&V side, all the way on the left side here, we don't know how to talk to our products initially, right? We just get them back. They're basically PCBs with some components on them. So we have to write a driver to actually interface with them. And so there's a lot of driver churn that actually exists. So when you look at the full gamut of all of these different silos, there's a lot of testing overlap that exists, and this is what we're trying to solve here at National Instruments, is how to support all three of these domains. And so I kind of talked about some of these challenges, and so in the past at National Instruments, we have rewritten tests to cover the different silos or different domains. And that's created some, this is basically our little mascot internally. And so then you kind of look like me at some point. I used to have hair on the top of my head, and now I don't. That's why I have a beard, so I can compensate for my baldness. And this is what happened to me, is that I worked in test engineering for several years, and so I have these issues. One of the other issues that we have too is correlating data across all these different domains, right? So if I have one instrument and I want to swap out another instrument, how can I correlate that data and make sure that I'm actually getting the correct data? And so this may be the last slide where we introduce the basic problem, and then we'll kind of deep dive. But basically, I have one product A, and I develop a test, and it doesn't have to be something complex, but it can be just measure a voltage or generate a voltage and measure it, or it could be something complex in RF like EVM for a particular standard. But once I develop it, I want to reuse it across all three different domains, and I want to be able to use it for several years down the road. Now, the goal would be that now that I've done this, and then I have the next product in flight, that I can reuse that across all of my different products, right? So if I did this, now my efficiency goes up tremendously. And now, instead of rewriting the same code as an engineer, I can actually focus in on the fun stuff, which is engineering stuff, innovating on the new challenges, the new products. The issue here is that our products are in different flights, and it's very difficult to look into the future to understand how you can develop something that not only meets your needs today, but meets your needs in the future. Okay, so that's kind of the basic problem, and what we've discovered is that in order to solve that, there's a lot of challenges that we have that are unique as far as solving this. And I've kind of talked a little bit about schedules and the different automations, whether it's manual or automated, completely automated. But really, the capital equipment is a huge care about for most customers, and especially inside of National Instruments, because we have several different products that we develop, whether it's single board Rio, whether it's Elvis 3, whether it's a DMM, an RF product, our Flex Rio, C Rio. We want to be able to leverage whatever we develop across a multitude of different instrumentation, different types of tests. And capital equipment becomes a big stumbling block. So if one product is using a $20,000 piece of instrument and another product is using a $50,000 piece of instrument, I now either have a couple of choices. I can either tell both groups that they have to buy the $50,000 or the $20,000, so I have to choose, or I have to tell both sites that they have to use both. They have to buy both. So now each product group now needs $70,000 in capital equipment. And that does not scale very well as far as being efficient with our resources and capital equipment. And so we're trying to, these are some of the challenges that we have, that we want to be able to swap out different instruments. And so what we've discovered at National Instruments is you have to develop a HAL and MAL that's truly flexible. And so when you kind of look at it, the idea here is that you have a VI on the left that just takes in two strings and gives you an output of a string. Very, very basic. And if I want to change that out with a different implementation, maybe it concatenates one, and the other one it concatenates it the other direction, right? What I do not want to do is I do not want to have to tell somebody that they have to open up the code and actually change the code in order to change the behavior, and then recompile that code and resave it. Because what that does is now I'm actually supporting two different pieces of code at the same time. Now when I start to deploy that on several different products, now I have to know where I'm deploying that and make sure that that if something happens, I have to go down and maintain that. So we believe that the key is that you need to have flexibility. Now in order to do that, you need to have known interfaces, and you need to be able to call things dynamically at runtime. And for anybody that uses LabVIEW, there's basically two different ways of implementing this in LabVIEW. Excuse me. You can use VI server or you can use a class architecture where things are dynamically dispatched. Internally, we've chosen the second one, which is a class architecture. So you can use VI Server to do exactly what we're going to show you. However, for the rest of the presentation, we're going to kind of ignore VI Server, and we're going to look strictly from a class architecture perspective. Okay, so kind of a real-world example of what this would look like. So on a lot of products, we have to make a measurement, and if it's just a 5-volt signal that we're looking at, we have two different instruments that can make that measurement. We can use a DMM, or we can use a DAC-MX product. And when you look at their drivers, they're completely different APIs, but at the end of the day, they each give you a scalar value, right? So I have 5.1 volts or something like that. And in order to get each instrument to make that measurement, they have completely different settings, right? So there's no overlap between the instrumentation that you have. And then to further complicate things, that the code looks completely different. So it's not really easy for me to extract out these different APIs. Now, you can see that this is now going to compound itself based on all the different NI drivers that we have, because each of the NI driver softwares are written specifically for that application of that hardware. And now we're also going to introduce third-party instruments into that. So how do we accomplish that? So another problem that we have at National Instruments is trying to figure out how to take a traditional HAL-MAL infrastructure and then put non-traditional instrumentation into that HAL-MAL. This is a good example here that if you take a traditional DMM, in this case it's a Keithley DMM, and one of our digitizers, what do you do with an instrument that overlaps both of these? So traditionally you would just have you would separate all of your instruments into their product class, if you will. And so when you have a unique instrument that overlaps that's very difficult to manage. The other thing is that you see this specifically on some of our more advanced products, right? Virtual bench. Virtual bench is, I don't know how many different instruments are in there, 7 or 8 different instruments, right? So you now have to either duplicate your implementation, or you have to figure out a way to manage this. Something else that's very unique and challenging is that when you have a traditional instrument, VNAs are generally a very expensive piece of equipment, but they're capable of doing quite a bit of different measurements. And so generally you want to have this set up on your bench. But when you go into a production environment or manufacturing environment, it can be very expensive to duplicate this on a test station. And so you can make the same type of measurements, whether it's an S21 measurement or something like that, with an RF power meter and an RF signal generator, or you can use couplers. But the idea here is you can use lower cost equipment to make similar measurements. This can also be done if you had just a source and you wanted to use a DMM to transfer the accuracy to your source. You can have a kind of like a feedback where you're measuring and you're adjusting your source output based on your DMM's measurements. And so internally, what we've discovered is that we need to abstract out the capability of the instrument rather than the instrument itself from a product class. And so how do we do that? So so basically what we're going to be talking about is a measurement abstraction layer, and this is where we're going to be talking more specifically about the capability of the instruments, or the capability of what you're trying to do with it, whether you're trying to source or measure something, and then how do you interchange that out with different pieces of hardware. Okay, so I talked a little bit earlier about the traditional DMM, and this is what a traditional HAL would kind of look like. So as you can see on the left, this is our NI DMM driver, and then you would have a third-party instrument driver here. And then typically what you've done for in the past for HALs is you have this DMM class up here, and this kind of outlines all of the different capabilities of a typical DMM. So range, digits of precision, power line cycles. I'm trying to think off the top of my head. But you can have all of the different type of settings up here, and then it would just know how to push those down to the different classes. So what we've done internally is we've made our HAL, or hardware abstraction layer, a lot flatter. Now it can be extended on, and we'll kind of show you that a little bit in a future slides, but we've basically made a flat structure for our HAL internally. And what we've done is we said that anytime you're talking to a piece of hardware, that is a hardware abstraction, right? So it doesn't matter what the instrument can do, we're basically saying that that is our HAL. So if I'm talking to an instrument via a third-party driver, whether it's Visa or through the Ethernet or some other means, USB, anytime I write a driver, we're going to put it over here in this class. And what you'll notice for the rest of the presentation, I'm hoping that we got everything done correctly, but you'll see that the driver is in blue to help facilitate when we talk about a driver class. And then you'll notice that the function class is also in green. And this is our measurement abstraction layer. And this is what we're talking about as far as the capability of an instrument. So a DMM can measure resistance, it can measure current, it can measure voltage. And so you can combine instruments to measure resistance. If you have a DMM that is a best in class at measuring voltage, and you have some way of sourcing some current, and you have a really good instrument, then you can do that. You can measure resistance, right? Ohm's law. And so instead, what we'll talk about how we can actually share these two classes together and how to implement that in LabVIEW. And this is just kind of showing you an example of an acquire voltage interface that we have. And I guess maybe I should kind of back up from terminology standpoint. We call it FCN, it stands for function. We just kind of abbreviate it so we don't have to write it out. And then ACQ for acquire, GEN for generate, and then DRV for driver. But this is what an acquire voltage interface would look like. So when you're writing your test code, which Ryan will talk about in a little bit, really you would just be looking at this VI right here, and it would just give you your voltage. So in the 5 volt example, it would just give you 5 volts. And you can see over here that we have a number of different settings. This is just showing you an example of what it would look like. So kind of taking our example of our two instruments, instrument A and instrument B, what we've discovered, and this isn't just with NI drivers, but we have a lot of experience with third-party instruments as well, that they kind of boil down into these different categories. And so you can see that generally you initialize your instruments, you configure it, and you do something with it, and then you make some kind of measurement, or it gives you some data. And then at the end of the day, you close out your instrument, because we're good LabVIEW programmers, and close out our sessions. And so what we've done is, this is what our abstraction code actually looks like from when we write our code. And so you would write your code on the function level, and so everything is dynamically dispatched, but essentially you would initialize your function here. You would have some generic settings that would be unique to acquire voltage, not to a DMM or not to a DAC device. And then I'll point out the commit. Ryan's going to talk about our commit in more detail, but the commit is the crux of our infrastructure, and it's a very important piece. And then you're going to read your data and then obviously close. So I'm going to pass it off to Ryan, and he's going to give you more detail.
All right, thanks. Everyone's still awake because we're about to dive deep. Let's take a big breath. Some oxygen. I'm going to back up really quick just to highlight this challenge here, right? You can see 3 different ways of writing this same measurement. And if you were doing a DMM or a DAC in the past, that's the kind of code you would have to be rewriting. Right? And this is the simple example. They get a lot more complex, right? Everyone has more complex examples than this, I'm sure. But our goal is to get to this bottom area where you write it once and change out whether it's a DAC or DMM under the hood. So you don't change the test code anymore. So that bottom level shows how tests are written against functions. You write to the type of measurement that you're trying to accomplish. Those functions call your drivers. So the MAL calls the HAL. So you can see here that we have driver instances, right? So you might have multiple sessions. You don't really know at the top level of the test, but a lot of things can happen here for abstraction. And then the functions actually call generic data operations on the drivers. And we'll get into more detail. I'm trying to show a real high-level view. Drivers implement the functions. So if you have an acquire voltage, it would be implemented by your hardware. This is what acquire voltage means for me, the DMM, or me, the DAC device. And you can extend them into the future because it's class-based. Without having to rewrite everything, you can rewrite the pieces that matter. Right? So that's the kind of 10,000 foot view, maybe not the 100,000. So the driver is probably the single most important piece of the flexibility we're trying to bake into this model. It is where all of the hardware differentiation goes. It is where a lot of the complexity and domain knowledge goes. How to use this instrument the most optimally. This is where you have that code. So when you look at this architecture, we're trying to keep layers above it lighter in implementation and putting more implementation here on purpose. That said, we don't actually want people to have to write a ton of code, so there is a set of functionality that a team like myself, who does more of the test tooling and infrastructure for the test engineers, we handle. And so that's what we're calling the baseline driver here. So one of the baseline driver responsibilities is to define the state. How do we handle state for hardware in a way that can be leveraged by NI to third party, right, and into the future? So you can see I've kind of highlighted what states kind of look like in that code example. On the hardware side, you're implementing what it means to be in those states for your hardware. So it kind of makes sense. Defining how we set and store, how we store and access settings. So make that consistent so that you don't have to rewrite that every time you sit down to interact with your hardware. So the hardware specific code has to handle what that setting means. The baseline driver will standardize how data is accessed on your devices. And hardware will decide how to overwrite those data operations. So I kind of flew through it. I'll back up a second. There's a state here, or there's the properties. It's kind of a common way of storing. And here's our data operations on the read. And I'll pause because I saw a couple cameras go up. I messed it up for you. So I'm going to go through those three concepts in more detail. So states, committing your settings and other things. So drivers implement standard hardware states. And I've got a drawing here as an example. And what this lets us do is it lets us make a MAL that can address this HAL layer in a consistent manner. Right? There's always a initialize, there's a commit, there's ways to do measurements, there's close. So you can see the cycle here is very, very basic, but it works pretty well. So you can see the initialize down in the code, commit, close. And what this lets us do is a pretty powerful state caching implementation, which I'll go into a little more detail in a bit. It might even be on the same slide, but I can't see what it is. So, but yeah, so now we can have the same states. So Rob said that commit was a very important piece of this, and he was correct. Commit helps us standardize how hardware acts in certain states. It helps us latch settings at specific intervals in your code. It lets us track the state of your hardware. So settings are basically pieces of your state. Are you set to acquire voltage right now or generate an output current? So this is an example I throw out there because I'm not a hardware guy. But so some of the benefits of queuing up a list of settings that we apply to hardware is that we can cache the state and track it at a high level, and then we can only execute the changes, which is really powerful. If you're sending 50 settings every loop of a parametric sweep, but only one of them is changing, it actually can take a lot of time to settle and change 50 settings, and not every driver or piece of hardware is smart enough to not do anything. Sometimes it will keep doing it. So this lets you say, oh, okay, you sent me 50 things, 49 of them are the same, I'm sending one element to the device, right? The other one is that it allows for atomic operations. So some drivers are actually really optimal, and you bought it because you want to take advantage of that optimization. So what you do is you say, I'm going to set 50 settings right now in one operation. I want to send it all at once, and the driver knows how to do that really fast. Maybe you put it in a string, you send it all at once. So if we do caching or if we do commits on a known cycles in your code, you can queue up 50 commands, send it to your hardware, and then your driver can send them all at once. It can be very optimal in how it handles those changes. And when you start breaking down hardware states into settings or lists of settings that you're queuing up and sending to any hardware, NI, third-party, things we haven't thought of yet, what it lets you do is it lets you store those settings outside of your code very easily. So now you're talking about a mechanism where you're kind of interacting with the hardware with a list of settings. And that list of settings could come from your block diagram, but probably better it comes from a file or a database. And so it makes a really easy system to start pulling those settings that are important for your test out. And what that lets us do is write one test, change the settings outside of that test, and not have to keep churning code or having code reviews or lengthy release processes, right? So this is a pretty powerful concept. So far, this has held to all the hardware we've thrown at it. It's a model that you can actually implement. Even if something doesn't know how to do state, you can add this layer on top of it. So here's an example of when you are actually implementing a commit processing in your driver. And it's actually a bigger image than maybe I wanted, but I'll walk you through it here. So this shows the commit, and on the left-hand side, there's a queue that we're pulling settings out of, and you can see we're just processing it in a loop. And you can see in the middle here, there's just a case structure. And that case structure says, I'm going to handle the setting settling time. And for the DMM, this is how I handle settling time. I take the double and I put it into this property node on the DMM's API. And that could be any instrument's API. It's just how do you handle that setting? How do you get it to your hardware? So it can look way different. You can see here that some of these cases actually handle more than one setting at a time. We call those coupled settings. I didn't put a TM on here. I don't know if it means anything to you, but when we go through, and sometimes you will run into a hardware device that has an API that will set 5 things at once. Maybe it has a connector pane. It says, I'm going to do these things all at once. I'll commit it to your hardware. How do you do that in a one-at-a-time type of situation? Well, you don't. It gives you the flexibility to say, I'm doing 5 settings at once. Another thing it lets you do is say, for this particular piece of hardware, if you set one setting, or you configure one setting, and then it actually coerces another attribute or setting on your hardware device, it lets you react. So you might have 5 in one case structure, because if you set any of them, they interact with each other in ways that you need to check. This is, again, back to this is kind of where the complexity goes if you're trying to make hardware more flexible.
Where you storing every one of those parameters in whatever class you are representing in DMM. So if you needed to make an DC range resistance one, only one changes. You know the state of the other four, you just pump those four on in.
Yes, so the question was, do we track all the states of these so that at the driver level you're not handling 5 if only one changed? And yes, we do. It's actually only things coming out into the processing loop here are the things that have changed. We've already calculated that. So that kind of segues into how we store settings, how we allow for hardware differentiation with these settings. So a quick note on functions. We went earlier and we said, here's a function and here's a known interface. It has all these settings, they have these names, and here's some read methods on it, right? That was our acquire voltage example. When you look at this, you can see that we wrote our particular test against property nodes. That's not a requirement, and it's actually something we discourage actively and do not provide for our driver layer. So while our MAL is very standard, our HAL is not as standardized, mostly because we're trying to flex it to hardware that is hard to anticipate what it needs to do and how it's going to accomplish what it needs to do. So drivers are not meant to be accessed in a super standard way. That's what functions are for. You're not writing your tests against the drivers, generally speaking. But you can access the settings, it's just in a more generic fashion. So instead of a property node, we can ask for the setting by name. It's a little more powerful for a driver who knows exactly what it needs to talk to and how it interacts with its hardware. So I'll go through another example of how this works in a little bit. So just a reminder of what these settings are and how we're storing them. That we're storing them consistently at all. I put the little screenshot up there on the right for those interested. It is a variant lookup in LabVIEW. We're just basically making a dictionary of settings that we're keeping track of, which means it can have a string as a key, and you can store any value in it. You can see here double, string, boolean, type def that you defined. It doesn't really matter. We cache it as part of the driver state. We only change we only commit what's changed. And there is a way to map these settings to functions. And I'll go through that in a second too. So, when we're talking about standardizing a MAL and how you handle allowing hardware to be different from each other, especially in settings, it looks something like this. So let's say we have a defined function setting. We'll call it source frequency here. And you have the acquire RF power function. And it says, I know what source frequency is. That's great. You come in with a driver called NI power meter. It also knows what a source frequency is. So everything's good. We pass a function from, or we pass a setting from the test all the way down to the hardware, and everyone knows what's going on. So let's say you get to Rhodian short power meter tomorrow, and it also has the notion of a source frequency, but it calls it something different, right? So it says, I know source frequency, I call it frequency. And this goes to the mapping. It says, when you say source frequency for acquire RF power, what that means to me, the Rhodian short power meter, is frequency. And that just automatically happens. So this lets us start differentiating. Let's say you have an undefined function setting. So you went to your acquire RF power, and you told it by string or a database or a file, set time percentage. And acquire RF power says, I don't know what that means, but it knows that it has a layer under it. And it says, well, what if the driver still might? And lo and behold, this NI power meter does know what time percentage means, and it commits it however it needs to, it implements it. And the Rhodian short power meter does not, and now it throws an error. So I'm going to pause here and just kind of walk through why this is pretty important. When you start looking out at why you even buy different pieces of hardware, they generally have a differentiator. Why did you pick a $20,000 instrument versus a $50,000 instrument? Sometimes just accuracy. Sometimes to get that accuracy, you actually have to set it up differently. It might have a new mode you have to put it in, right? And that's a different setting that you have to set. That setting was not anticipatable at a acquire RF power level. That was completely new concept, and unless I have something like this that lets unknown settings flow through your design, then you're going to have a monster list of settings in your measurement abstraction layer that continually grows year over year, or you have some governance committee that makes sure that, do we add the right ones, and I'm sorry, I didn't get your really specific setting in, change how you write your test completely. That's just what you're going to have to do today. So this keeps more people on the standardized test format and lets them basically change what settings are flowing through their test without you changing the test code. Said I was going to go deep, so hopefully I don't lost too many. So here's an example of the driver definition. I said we map settings from functions to drivers. Here's an example of that. You can set, our driver definition files actually handle a lot of the behaviors of the configurations, the boilerplate for a driver. It does things like, how do you instantiate the class? Some drivers can do a single session and some can do multiple sessions at a time. It sets the default values, and I'll show you here. In this case, you can see acquired voltage on our DMM. And you can see settling time at the top was actually a direct match between acquired voltage and this piece of hardware. They both have the same concept and the same name. You can see these yellow ones, they had the concepts, but not the same names. And then you can see a whole lot that are ignored here. And that says that as a driver developer, I acknowledge that for acquire voltage, this was a setting that you recommended that I implement, and it has no meaning to me, and it doesn't matter. I don't care. I intentionally marked it as ignore. Now, if I don't go in and set one of these three scenarios up, if you just didn't put a setting from the acquire voltage in, it would actually error. So what this helps us protect is, what if you did change acquire voltage year over year? We don't want it to accidentally work in test. We want to make sure that if you are using a driver, that driver was at least anticipated all the settings it's supposed to be handling. So, does that make some sense? A little mapping there. Okay, so the last concept I'll go through before I hand off to Rob is the data-centric, the data operations aspects to our drivers, and why that's important. So the driver class is kind of built around the states, the settings, and these data operations. And the root level driver class has methods around data type that is being returned or written to or acted on by the driver, by the hardware. So some examples here are read waveform, or write 1D double, or do some action with a variant. So in a little more detail, here's that same picture again. And you can kind of see on the left-hand side what the measurement abstraction methods look like. You have read, maybe enable output on the generate voltage, you have measure maybe, and then on the driver you have read, write, and action. And it seems super simple, and this is where it's just a little bit of standardization. It actually helps us quite a bit in this kind of a model. So let's go through the read example. So here's a function read to a driver read. This is the MAL calling the HAL, which is what I said earlier. So we have acquire voltage read, and we have a driver read at the top. So acquire voltage read sends a string to the driver. It calls driver read, and it sends a string called, it's really hard to read, but it matches the little bullet there. It calls act voltage read. That string is sent to the driver read. And then the driver read for driver ABC looks like this. It takes that type that was sent in its read, it puts it in this case structure and it says, oh, okay, you're asking for a voltage. This is what a voltage means for me, the hardware. And you can see I have the DMN API, it pulls out a voltage and it returns it. And so now, let's go and implement another function. So some of the power of this architecture is this one piece of hardware can actually be used in many different functions. So for this DMM, here's a gen voltage. Maybe that's a bad example. I'm kind of a dunce here, but that's fine. So you can see up at the top, we have our function call, and it does acquire voltage read. And then here's our implementation at the driver level that takes the string out, gets ACK voltage read, and it returns a voltage. And now I'm going to go and I'm going to extend that same piece of hardware with one new function, and that new function is gen voltage measure. You can see at the top, gen voltage measure called read. It's actually trying to return, I guess, the output, or what it is outputting. So at the top, it actually calls driver read again, that top level function. It sends in the string gen voltage read, and now I have a new case structure. So to add one new function to this driver, I added one case structure. So this extends pretty well. I didn't have to write new test or VIs. I didn't have to do new classes. I just went to this one VI in the commit, which is why it's so important. You go to the commit VI, extend it to what it needs to do. I say the read VI in this case, and then implement what's needed. So with that, I will go back into Rob with the ecosystem.
All right, so now we're going to talk about what this looks like from an ecosystem perspective, and this is kind of based a little bit on what we do internally at National Instruments. So before we go into what the ecosystem currently looks like, or in the future, just kind of some lessons learned that we have discovered over the years of probably doing this, and you may have experienced some of these same issues. Number one, we kind of see two pitfalls to HALs and MALs in general when we develop them. Number one is not creating the ability to have flexibility into your structure or your architecture. Ryan kind of mentioned this. There's a reason you spend extra money on that really nice piece of equipment, because it does it faster, right? Faster means more money, more revenue, right? So you want to take advantage of those capabilities. Potentially it has a new setting that was not supported in the general structure, so you don't want to have to wait for a standards committee to add a bunch of architecture or setting in order to start using it, right? You want to be able to buy it. It comes in, and especially as an engineer, it's kind of like Christmas morning, right? You buy a $50,000 piece of instrument, you want to start using it. At least I do as an engineer. So you want to be able to have flexibility built into your structure, and if you don't do that, that's generally one of the pitfalls. One of the other pitfalls that we have discovered, especially talking to some external customers, and we've experienced this internally, is central ownership. So what we're talking about here is not having people oversight, not having people review code. We completely agree with all of that, especially source control. I'm a big believer in source control. But what we're talking about here, central ownership, is that there's a small team for the entire company. So National Instruments is a large company. And so what we don't want to do is we don't want to have 5 people that are really smart and they have to figure out all of the tests that the entire company is going to make over the next year, or in every single measurement, in every single permutation of every single setting of hardware and everything to get that done, right? We want to be able to distribute that to the domain experts, if you will. Okay, so what does that actually look like here at National Instruments? So this is our same function and driver infrastructure that we kind of talked about a little bit. And Ryan is part of our test services team, which is more of our architectural team. And so what he's looking for is these high-level driver classes functions, right? And how they interface between each other on the function level. So his group is mainly focused in on this blue area. Then you get a group of engineers, whether it's V&V engineers, somebody in the metrology space, test engineers, or another analog engineer that really understands the hardware and how to make a measurement. right? And this is the red domain, and this is kind of the group that I kind of fall under right here. So I know how to set up a DMM to make it a very accurate measurement, and that is something that we want to duplicate. We want to hone in on the ability of the instruments, especially when you start spending a lot of money for it. We want to take advantage of it. And so you can see that this red box is kind of the group that I would be kind of overseeing. But what you'll notice is that there's these purple, the functions. And so both groups coincide, and we both agree on how the architecture will interface with drivers, right? And so both groups are now talking, so now we understand how the whole structure works. And so the test services team is could be a central location. I definitely highly recommend it. And so that could be a small team, but they're looking more from a high-level architectural perspective. If you came to our other presentation that we talked about on Tuesday, we also built this so it's a plug-in architecture. So if your settings can come from a config base, and let's say we have a new database that we want to implement, Ryan's group would be in charge of implementing that plug-in architecture. But then how do we validate the settings for a particular piece of hardware to make sure it's making that measurement? That's where the central domain expertise would be there from a test domain. So as an example, I'm in the RF group, and so I would be kind of looking at all the RF products, making sure that all the RF products from a hardware perspective are actually being used correctly to make that measurement. And so we're kind of saying that instead of having one central team, you need to make sure that you're capitalizing on the different domain expertise that you have at your company, and this is how we've set it up. Now, the whole idea is that we don't want to rewrite tests. We want to be efficient. We want to get to market faster. We want to be able to produce more products for you, our customers, and we want to be able to swap out instruments and so forth. And on Tuesday, we had a good case study on how we did this, and we don't have it in the slide deck, but by implementing this architecture that we have here, we basically cut our several months off of our project schedule, and we actually delivered a better product because we were able to do more testing than originally anticipated, which is kind of interesting. But what we want to do is we want to create this ecosystem. And so basically, you'll kind of hear other presentations talk about this, but somebody is going to develop this test or this driver or this function, whether it's the test architectures team, Ryan's team, or a test domain expert, the RF would be me. We develop it, and then the idea is that the whole company would then be able to use it. And so you could, now, once I've developed it and I've kind of, yes, this driver is actually doing what we think it is as a test domain expert, now other groups can now use it, right? They can now consume these components. And then once it gets into this library of components that have been approved, now other people can start developing on it, right? And so if we have 10 test engineers underneath of it, they can just know that I'm just going to go to this library and I'm just going to start using it, and it's just going to work because the test domain experts have kind of approved it. And then we do have, especially source control, big believer in source control. But we have exports of our code and our libraries and everything. And so if anything needs to be modified, our infrastructure allows for that. And then the idea here is that this ecosystem kind of is self-sustaining, right? Once we get it out there and people start using it, if there are issues, we can quickly modify it. But really what we want to highlight here is that we put all of our energy into submitting new components. So once we've done all the work for a specific driver, whether it's a third-party instrument or an NI device, we basically want to have a really good quality control going in here, right? Looking at the code from a review standpoint, and we submit it into this ecosystem. Once we get it into the ecosystem, we're now enabling the rest of our company to be really efficient, and that's really what we're trying to implement here in the test engineering group. Okay, so one of the things that we've been talking about is functions and drivers and how we do this, and this is kind of a slide that we've kind of implemented. I'll walk you through the slide a little bit, but what we want to show from a high level is that we've only been talking about a very small portion of our HAL infrastructure that we have internally. This is what a code would look like that we would develop. We develop it so that it can run standalone from a bench perspective, or it can be run in test stand with little to no ease, because we want to be able to take that analog engineer V&V perspective and be able to automatically push it into a production test. That way the data correlates, right? That's a big issue for us. And so you can see here at the top left over here, there's different ways of having configuration, whether it's Excel, an INI file, whether you have a database. It's a plugin architecture, so you can pick which one you have. We've kind of standardized on using Excel because a lot of people have access to that tool at our company. We want to be able to easily add switching and fixturing, message pop-ups, everything be within the code, whether you're doing standalone at a bench, and this pushes all the way into the metrology space as well. And then we want to be able to log the data in a standard format. We don't want to have people rewrite code on how to log data and how to compare it against limits. So we have all this written in LabVIEW. These are our common pieces. And then down here, really this is what we're talking about. This top layer, this red layer, is our toolkit layer, and this kind of handles everything. This is the high piece that the architecture team kind of handles for us. And then the actual HAL and MAL is actually down here in these two VIs. So when you look at it, if I have to create a new VI or a new test, essentially I get all of this stuff for free, and my code looks very small, right? And then there's another piece here that we really care about here at National Instruments, which is warm-up time for our products. And so we have built in the ability to have remote and local instrument control, which is another cool feature. So that allows us to have two chassis with two controllers talking to each other, and so one controller is able to run code on another controller and so forth. So this allows us to not power down our instruments from a warm-up perspective. Yeah, okay, so I think we went a little long, and we're the last session, so we're basically keeping everybody from leaving and getting to the airport potentially. So we will now open it up for questions. So what questions do you have, or might you have? Okay, there's a couple. So
Is the idea kind of you can take any device and then call it any of the functions that you've outlined in there? There's got to be some conditions in there where obviously a function, you kind of mentioned for a second that the DMF generating voltage maybe was a bad idea. There was a read buried in there. There's got to be like some no-op conditions, because someone's going to go generate a sequence when they're testing a product, right? They can throw down a generate on something that has no idea what a generate is. Was there buried no-ops, or how is that handled?
Yeah. So
there's not a lot of pre-checking just yet in our infrastructure, because it's a really challenging problem that everyone struggles with. But in that case structure, if it's not handled, if it sends something it can't handle, the default behavior is to error. So you get a runtime error if it's not implemented. So if you sling something down that doesn't know what generate does, under the hood,
So it's back to the user to say, hey, this isn't valid, or get out of my sequence.
Right, you probably wouldn't get to the read. You would probably have errored way earlier on the settings, which would have been associated with that function.
yes, I just want to add real quick. So this is our internal. So so currently there's kind of some assumptions, and I think this was said at one of the previous session. We're kind of assuming that people know somewhat what they're doing with this architecture. So
you have like a list of attributes for a function, or I guess it's a drive. I think it's a function. But anyway, I mean, I guess when you come up with a new instrument that defines a voltage measurement, you have to add to that attribute. Is that right?
right. So
I mean, do you worry about like proliferation of those attributes? I mean, you keep adding new instruments, and it just keeps getting longer and longer, and you can't figure out what you
So the question was, when you have a new instrument, it has a new capability, do you add that back to the function definition of what settings are available, right? Okay. So the idea is, hopefully not a lot of the time. Just because the hardware can do it doesn't mean that it makes sense at a function level. That becomes the discussion that kind of was that overlap between my group and Rob's. But the idea is that if you do have a new function or a new setting, you either expect it to come from some sort of configuration when you're using that instrument. Again, kind of expect that people know the instrument they're about to be using with their test. Or you automatically calculate the new setting, maybe based on existing attributes that come down, or you have a big discussion about, okay, maybe we need that one more attribute. But the hope and the idea is that you don't add 100 more settings over time onto an acquired voltage. That actually stabilizes and settles for your use. And if you're wrong, the actual expectation is that at some point you don't keep extending acquired voltage, you make some new measurement. Just make a new MAL layer and you start implementing a new case structure in your weeds because your designs have evolved. We're going to be able to share some examples of our external code. I am pushing those requests to business cards, please. If you could come to the front afterwards and give us some business cards. There are potential opportunities for this.
In your previous presentation, you had mentioned that sometimes you may use one instrument, like on D&D, use one instrument, and perhaps you might use a different instrument or two instruments together. Where would prioritization and what instruments you use or a combination of instruments fit?
So where does the prioritization of deciding between using one or multiple instruments in each different test group?
Correct.
Correct.
Yeah. So I'll talk a little bit about some of the unique things we have in the RF world. One of the things is that, as an example, we have acquired RF power, and generally what we'll do is to get the accuracy, we'll use a power meter, but they don't have the dynamic range, and they're generally pretty slow. So we can use a spectrum analyzer to make a similar measurement. And this goes back to an example where you would have an untraditional instrument working with a different type of measurement. And so the decision maker is the person that's implementing the test, right? So it would be the test engineer or the analog engineer, and they would have to choose. But what you would be able to do is you'd be able to send in additional settings for the spectrum analyzer to set it up to make a similar measurement. Now, in doing that, you have to be aware of the accuracies that you have, because the spectrum analyzer may not be as accurate as the power meter at that particular time. So it may give you a similar type measurement, but the decision maker is the person that's actually running the test. In this case, and this is all internal, right? And so internally, this would be if the test engineer is using a spectrum analyzer on the production floor, and maybe they're correlating that to a power meter or something like that, and the benchtop or the metrology space is using power meter. It's whoever is in that space gets to make the decision on what instrument they're currently using. So it's not forced upon anyone, but that instrument has to have that capability internally. Does that help answer the question or no?
Well, if there's two instruments connected on your bench that both can do your required voltage measurement,
Right.
what is a property passed through the acquired voltage indicating which one should be selected?
Okay. Okay. So yes. So there, behind the scenes, the toolkit which we showed here at this top layer internally, which we didn't really get into in this presentation because we were really talking more about our HAL mount. But internally, this toolkit layer handles all of that communication. So it will handle the knowing if the session is open, and then it will also know the state of the particular hardware. So potentially you could have two pieces of hardware open, and what you would have to do is you would have to, in our terminology, you would give it a tag or a unique alias and say, I am talking to this piece of hardware for this instrument. So if you had 5 DMMs in your system, and they're all the same NIWeek DMM 4071, which one am I actually talking to? And that may be different depending on the switch fixturing and so forth that you have. And so you have to know that as a developer or implementer.
So you can see it right here, actually, there's an instrument array that comes in, and it is defining for acquire voltage, you are using this instrument today. And that instrument is the driver code that was implementing that interactions with the hardware. And you can see here that alias aspect. So when you initialize these functions, you give it an alias or a tag. And so now you can pull it out like this is my device that under test, and that's how I'm going to address it. Or this is the source of the sync for my test, or whatever you want to call it. And that's how you make that mapping. All right. There's too many questions, so I'm going to have to call it for today. If you do have more questions, feel free to come up. We'll stay around for a little while. Thanks.
Because you're saying this is
and I define that because your station is this is a little bit weirder these days because I have 8
Well, there's but that's really tough because one, there's a lot of the foundation. Your overall measurement is a little bit more difficult. There's one thing that we did. We have it's not easy. That's the thing.
Yeah. I forget about the service.
Especially with like a distribution, what's we currently don't do that. Okay.
It is a different paradigm.
So I mean, at the point in time where you're not ready to test here. We were early on this. This makes sense.
right. I think there's a lot of
And that's because it's itself. You're sitting in it. Sounds like, I mean, so yeah.
So one of the things we use is
Yeah, I don't know.
my experience.
Yeah, but I mean, I've done it like
So one of the
they didn't. I know. It was like over dinner that night. It was like, oh, that's way different.
Well, this is like
Yeah.
we're currently doing that. Makes it very
The organizational side.
we didn't really show. We just have
Yeah.
I think the pushing arms.
All it did was say, but on the other side, and then you don't have to use the real So I think,
Yeah, no problem. Absolutely. Flight home, perfect, right?
well, if you want to compare anymore, we still are in
yeah, we will. But this is very interesting. So thanks. Have a good one.
Yeah. So there is a
I had to cut so much from this. I wish there's things like how you do
what Brian and I were doing was just internally and we're just kind of showing customers what we're doing kick off the
That is nice. I'm doing
but there are some opportunities as well. If you have a business card, I can take it and I can pass it along.
Yeah.
They help you with the.
Oh, yeah, with the web service stuff. Yeah. Or with web services or something to do with TCP.
Oh, yeah.
Yeah, and the question.
All right.
Yeah.
Yeah, thanks for sticking around. It's the last day of this.
Yeah.
Gotta take advantage.
That's right.
Yeah.
That was fun.
Yeah, it was a fun. It was a fun tour.
Once,
Oh, yeah.
I remember correctly, that's the one where I was wading through all the code at 2017 to try to find where that error was possible coming from. And then I reread and actually,
Yeah.
I actually read what you wrote. I'm like, this is 2011.
Okay.
Completely rewrote everything between 11 and 15 or 17.
Yeah, we can consider it now.
Okay, yeah. Yeah,
I would definitely be interested.
Okay, I'm more than happy to pass this information on. This is just internal, because we're like every other company, right? I think,
Things going well other than that.